everyone. In this video, you are going to learn how to find values and characteristics of functions from a graph. So we've been focusing a lot on functions algebraically, meaning that you're given an equation, and now we're going to move into focusing on graphs of functions. Okay. So let's start with evaluating functions graphically. Well, remember that if you're given h of 3 equals 2, that means that when x equals 3, y equals 2. Okay, because remember that function notation. This would be x of x equals y. Instead of f, we're just using h to name the function. Okay. All right, now we are given the graph of two different functions. So f of x is the dashed line graph, and g of x is the solid line graph. So you do have to kind of try to keep those two straight. And it might be helpful to maybe label them on the coordinate plane. So up here we might say, okay, this is f of x, which is the dashed line graph, and then this is g of x, which is the solid line graph. Okay, so when evaluating functions graphically, you're trying to basically find the y coordinate of the point given the x coordinate. Okay, so if I'm finding f of -1, then I would go to -1 on the x-axis, and I would go up to the dashed graph and over to y, and I would see that f of -1 equals 6. Okay, let's say we want to find f of -9. We're going to go to -9 on the x-axis, go up to the graph, and I'm noticing we have an open circle there. So that is actually telling us that f of -9 is undefined. It is not defined for us because there is an open circle in the graph. Okay, let's say we want to find f of 5. So here's 5 on the x-axis. Well, remember f is the dashed graph, so this time I actually have to go down to get to the dashed graph, and then I'll go over to the y-axis, and my y-coordinate is -5. Okay, now we're going to switch functions. So now we're going to look at g, which is the solid graph. Get rid of some of this. So let's say I want to find g of -3.2. So I'm just going to have to kind of approximate where -3.2 is on the x-axis. I know that it's between -3 and -4. So let's say it's maybe about right here. And this time we're going to the solid graph, because that's the graph of g. And then I'll go over to my y-axis. So again, I'm just going to have to approximate that value. It looks pretty close to 1.8. And anytime that you are approximating a value, instead of an equal sign, you can actually use a symbol that stands for approximately. So in this case, we're saying g of -3.2 is approximately equal to 1.8. Okay, and then g of -11. So here's -11 on the x-axis. I'm going to go down to the solid graph. And I do have a solid circle, okay? So this point is actually part of the function, so I can evaluate the function at -11. Just go over to your y-axis, and my y-coordinate is -2. All right, and then g of 7, okay, here's 7 on the x-axis, go down to the solid graph, over to y, and I can tell my y-coordinate is -1. So when you're evaluating functions graphically, just remember, given the x-coordinate, you're just trying to find the y-coordinate of that point on that particular graph, okay? All right, we can also perform operations graphically. So you may remember when we were doing this algebraically, we learned that f plus g of 3 is equal to f of 3 plus g of 3. So then we just have to evaluate each function graphically, and then we'll just add the two numbers together. Okay, so again, remember f is the dashed graph, g is the solid graph. So to find f of 3, here's 3 on the x-axis. I'm going to go down to the dashed graph over to y, and f of 3 equals -6. And then I'm going to find g of 3. So this time, I'm going to go up to the solid graph and over to y. And my y coordinate is +6. And then if I add -6 plus +6, we get 0. Okay, the same thing works for subtraction. F minus g of -3 is equal to f of -3 minus g of -3. So again, we're just going to evaluate each function graphically, then we'll subtract. All right, so to find f of -3, here's -3 on the x-axis. F is the dash graph, so I'm going to go up to the dash graph over to y. And I can see that f of -3 equals 6. And then g of -3, so again, here's -3, stop at the solid graph this time, go over to y, and I can see that g of -3 equals 2, and then 6 minus 2 equals 4. All right, now I'm just switching things around, g minus f of 9, so remember that equals g of 9 minus f of 9. Okay, let's find g of 9. So here's 9 on my x-axis. I'm going to the solid graph, over to y. My y coordinate is -3. Okay, minus, and I couldn't help but notice when I was doing that this particular point is on both the graph of f and the graph of g. So they're going to have the same y coordinate. So I'm just going to end up with -3 minus -3, which again will end up equaling 0. Okay, then we can get into, some more complicated operations. So in the next example, we have 2 times f of -4 minus g of -6. So this will become 2 times, and then I'm going to go to my graph, evaluate f of -4. So here's -4 on the x-axis. I'm going to go to the dash graph over to the y coordinate, and I can see, or the y-axis, and I can see my y coordinate is 6. Okay, minus, and I have to find g of -6. So here's -6 on the x-axis. I'm going to go down to the solid graph, over to the y-axis, and I can see the y coordinate equals -2. And then I'm just going to follow order of operations. This will end up equaling 12 plus 2, which equals 14. All right, our next example, g of -8. All right, here's -8 on the x-axis. Go down to the solid graph, over to the y-axis, and I can see my y coordinate is -2 plus f of 0. Well, here's 0. I'm going to go to the dash graph, and I can see my y coordinate is 3. And then g of 0, okay, if I just keep going up a little bit more to that solid graph, I can see that g of 0 equals 4. -2 plus 3 is 1 over 4. Okay, next example, we have -2 times g of 8. To evaluate g of 8, here's 8 on the x-axis. G is the solid graph, so let's go down to the solid graph, over to the y-axis, and my y coordinate is -2 minus 3 times, and then f of 11, okay, here's 11. I'm going to go to the dash graph, over to the y-axis, and I can see that f of 11 is also equal to -2. And then we're just going to work this out. Negative 2 times negative 2 is 4. We end up with plus 6. 4 plus 6 equals 10. Okay, now what I want to show you here is that we can also switch things around. So this time, notice, we want to find the values of x such that f of x equals negative 6. And remember that f of x equals y. So this is telling you that y equals negative 6. And you're trying to figure out the x values. So the easiest way I find to do this is y equals negative 6. That's the equation of a horizontal line. So if I want to draw this horizontal line, and remember that f is the dashed graph, I'm looking for the values of x where the dashed graph intersects that horizontal line. And I'm noticing that only happens at one point, and the x coordinate of that point is 3. So this would be x equals 3. Okay, let's go to the next example. The values of x such that f of x equals negative 3. So again, I'm going to draw a horizontal line at negative 3, and I'm looking for where the dashed graph intersects that horizontal line. And I can see that that happens when x equals 2 and when x equals 9. And you guys, this might be a case where we use that set notation. If there is more than one solution for x, we might use the curly braces and then just put like 2, 9. All right, next example, the values of x such that f of x equals 6. All right, so this is kind of interesting because notice, this dashed graph is horizontal. And so if, I did the same thing and I drew a horizontal line through 6 on the y-axis, like that intersection is going to happen at more than just like single points or single values of x. So in this case, our answer would actually be an interval, okay? So we would say that the values of x such that f of x equals 6 would be from negative 6 to negative 1. And we would need to use brackets because we need to include those x values, okay? We need to include those endpoints. All right, let's switch graphs now to graph g of x. I'm going to erase some of this just so we can see it. So now we want to find the values of x such that g of x equals negative 6. So again, the idea is I'm going to draw a horizontal line at negative 6, and this time I'm looking for where the solid graph intersects that horizontal line, and I'm actually noticing that it doesn't. So we can just say none or no such values of x. Or this is also a case where you might use the null set, the symbol for the null set or empty set. Okay, next we want to find the values of x such that g of x equals negative 3. So again, I'm going to draw a horizontal line at negative 3. I'm looking for where the solid graph intersects that horizontal line. And I'm noticing that only happens at one point, and the x coordinate of that point is 9. So x equals 9. All right, find the values of x such that g of x equals 4. So again, I'm going to draw a horizontal line at 4. I'm looking for where the solid graph intersects, and I'm noticing that happens at 2 points. And those x coordinates are 0 and 4. So again, we might use set notation to indicate those two values for x. Okay, now sometimes we might compare function values to 0, okay? So which variable, x or y, does the function notation f of x represent? Well, remember, f of x equals y. So it's important to always keep that in your mind. So if f of x equals 0 for a given point on a graph, then where is that point located? Well, that would mean that the y-coordinate is 0. And if you think of your coordinate plane, if the y-coordinate of a point is 0, then that point is going to be on the x-axis. Okay? So this point would be on the x-axis. Okay, if f of x is greater than 0 for a given point on a graph, then where is that point located? Well, this is like saying y is greater than 0. So that point would be located above the x-axis. If f of x is less than 0 for a given point on a graph, okay, again, that would be like saying y is less than 0. Then where is that point located? It would be located below the x-axis. Okay. So just to show you this in a picture, for f of x to equal 0, again, that's saying that y equals 0, we would just be finding the x-intercepts. So then if it says identify the x values for the highlighted portion of the graph, because we are identifying singular points, we could use set notation and we could just say x equals, and it looks like -3, 0, and 6. Okay. Let me highlight the portion of the graph where f of x is greater than 0. So again, we're looking for the portion of the graph that is above the x-axis. So I'm just going to highlight the portion that is above the x-axis. But so to identify those x values, does it make sense that we'd have to use an interval? Because honestly, the x values are infinite. Okay, so we're going to use the endpoints to write our interval, but then you have to think, would I use brackets or parentheses when I write that interval? Well, notice your inequality sign is only greater than. So if you include the endpoints, that's when f of x equals 0. Okay, so we actually don't want to include the endpoints, meaning that we're going to use parentheses on our interval. And so we'll just say f of x is greater than 0 from -3 to 6. Okay, highlight the portion of the graph where f of x is less than 0. So again, that's where the graph is below the x-axis. Okay, so this time I'm going to have to write 2 intervals. And because I'm using the endpoints of the graph, which are both closed circles, I would want to use a bracket for the endpoints. So it would look like this. My first interval would be a bracket, -5, comma, -3, parentheses, and then we could use our union symbol, and then we'll pick that back up, parentheses, 6, comma, 7, bracket. And again, the reason I'm using a bracket on my endpoints is because those are actually solid circles, okay? And I'm using parentheses at these points because I don't want to include these values. Because at those particular points, f of x equals 0. F of x is not less than 0, okay? Now, you guys, that might change if your inequality changes. If this was f of x is greater than or equal to 0, then I would have used brackets here. Same thing here. If it was f of x is less than or equal to 0, then I would have used a bracket on the -3 and the 6. Okay, so pay attention to your inequality sign. All right, and then sometimes we might compare 2 functions to each other. I feel like I'm missing something down here. No. Okay, when we compare 2 functions to each other, which variable x or y do the function notations f of x and g of x represent? And again, the answer is y. So if we're looking at two graphs and we're trying to figure out where f of x is equal to g of x, then what are we looking for in the graph? Well, hopefully you're recognizing we're looking for points of intersection. The points where the two graphs intersect. If f of x is greater than g of x, what must be graphically true? The graph of f of x is above the graph of g of x. And then if f of x is less than g of x, what must be graphically true? F of x, meaning the graph of f of x, is below the graph of g of x. Okay, so let's look at some examples. And actually, before we get to the examples, I want to emphasize that if you are comparing two functions, we're comparing f and g, we can only compare those two functions on the interval where they both exist, okay? Because that is the interval of values, where both graphs exist simultaneously, okay? F of x and g of x can only be compared on the interval where both graphs exist. All right, so let me. Okay, so if we're comparing these two graphs, and again, f is the dashed graph, g is the solid graph, then notice that f, which is the dashed graph, starts when x equals -4 and ends, when x equals 7. And then g, which is the solid graph, starts at when x equals -5 and ends when x equals 7. So, like, these two graphs only exist simultaneously from -4 to 7. Okay, so we can only compare those two graphs from x equals -4 to x equals 7. Okay, so let's say we want to find where f of x equals g of x. Again, we're just looking for the points of intersection of the two graphs. So I can see that the graphs intersect here and here. And we're identifying the x values. Again, those are just single points, so we could use set notation and just say x equals -2 and 5. If we want to find where f of x is greater than g of x, again, we're looking for where the dashed line is above the solid line. Where is the dashed line above the solid line? So I'm noticing here and also here. The dashed line is above the solid line. So in that case, to identify the x values, we have to use an interval. And in this case, we're going to have two intervals, one for each part of the graph. So we would say from -4. Now, because there's an open circle in the graph, I'm going to use parentheses. So -4 to -2. And I'm going to use parentheses because when x equals -2, f of x equals g of x. And we're just focusing on where f is greater than g. All right, and then we can use our union symbol. And then our next interval would be from 5 to 7. Bracket on the 7 because of the endpoint that has the closed circle. Okay, now we want to identify the x values where f of x is less than g of x. Okay, so we're looking for where the dashed graph is below the solid graph. So that would be here, here, here. And so we can actually write this in one interval. Those x values would start at -2, not including -2, because remember we said over here that when x equals -2, f equals g of x, comma, and then it stops when x equals 5, and again, parentheses, because again, when x equals 5, f equals g, it is not less than, okay? But I do want to stress, if we change those inequality signs to greater than or equal to, less than or equal to, then we would have to change some of those parentheses to brackets, because in that case, we would include some of those x values in the interval, okay? All right, you guys, so we will stop there with interpreting graphs. I know that was probably quite a bit of information. You can probably see why I put this into 2 separate videos. But we'll definitely practice some more in class tomorrow. And as always, thank you for watching, and have a good night.